worked with power series. Power series with respect to variable x, as usual. Talk about the conversions on the parts of number line. So let us try to illustrate this by looking, let's say, at exercise number 15. If you have any exercises in mind, please let me know. I'll do my best to solve those today. So problem number 15 has a series with a denominator that has n factorial, and the numerator of this series has x raised to the power of 5n. And it starts at 0 and goes to infinity. So we're not going to use absolute values here because we know that n is positive, but for values of x, we actually should, and test that I'm going to use will be a so-called ratio test, definitely not a root, because factorial and the nth root are not really very friendly with each other. So we're gonna deal with the n plus first term divided by the nth term. And from experience, we already know that this n plus first term should be factored in such a way that this nth term will be canceled or partially canceled, and that would be a big help for us. So for the n plus first term, I need to replace my index n with n plus 1. So denominator nicely factors with n factorial times n plus 1. And for the numerator, when I distribute 5, we'll get a fifth x raised to the fifth power, actually 5n power, and then multiplied by x raised to the fifth power. So this 5n powers and n factorial on the bottom is what I really needed to be able to cancel with my nth term pieces. So that's why we do this separately, so I don't have to carry it throughout this entire limit and the fraction. And now we're going to do the, I guess I'm going to write this down and then cancel. So x power of 5n. I know that people get used to this and write it much faster. And I'm sure after you do a couple of exercises, you will also be able to do this faster. Well, my goal is to show you how to do it correctly. And if you want to do it faster, if you know how to do this correctly, then definitely you can use any way that you prefer. So what I already can see that these two fractions are gonna cancel each other out. And then what happens in the next step? Well, looks like the limit that I left with is gonna be 0, right? So limit when n goes to infinity of, we used to put the absolute values, so I can say that x to the fifth, which is some number that does not depend on x, multiplied by 1 over n plus 1 is gonna equal to 0, because this is 1 divided by big, and that goes to 0 when n approaches to infinity. And this is great because it means that x doesn't really matter. It's smaller than 1 for all real values of x. So for all real x, which means that the series is convergent at any point x. Let's say, really? Well, try x equal to 5,000 or -1,000,000 or 1/2, or just put any number you like instead of x and see what's going to happen. Your series will have its sum equal to some finite number. I'm not gonna try it, but you can always check this out, because no matter what real number you use, the series is gonna converge what real number you use instead of letter x. And that's what we just shown by using this special test. And I guess that makes the exercise to be very nice, because usually we experience some issues with convergence, but not here. So whenever n factorial is in denominator, it's very strong function that makes everything to converge, and that's the point. If it's a numerator, usually it's vice versa, then everything is gonna probably diverge. You can try exercise like number 17 and see what happens with n factorial is now in numerator. So those are not that interesting. I guess more interesting will be when we get some interval for conversions. So let me try something without this n factorial, and looks like there are plenty of exercises of that kind. So let me try problem number, let's say 27 or something like that. So maybe I can try to get room for this, and let me share the board. And a good thing that at some stage you notice that these problems again are all pretty much of the same type. And so you do a couple of these problems like we did last time, and then today we do some more, and then we should be able to do any exercise here, because they're all of the same pattern. So here's the series. You multiply by -2x in the parentheses raised to the power of n-1. So what people do sometimes is they take out that -1. They actually kind of ignore it, because that'd be a -1 to the power of n-1, and then it's multiplied by 2x raised to the power of n-1. Right? You can split this portion here, because when you be considering the test, again, n plus first divided by the nth term, then we take the absolute values, so this -1 is going to be ignored. So let's see what's not going to be ignored, because we take absolute values. So I can list the n plus first term to help me start thinking about this. So we have n plus 1 here, and then plus another 1. And then I'm gonna not to worry about this, because I take the absolute value. So just 2n raised to the power of n plus 1 minus 1. Like that. Okay, so let us set that limit. Now, see what happens. So we got the fraction with a numerator that has all of this stuff, and this is actually n plus 1 over n plus 2, right? And then we'll also have 2n raised to the power of n. So maybe in order to be able to nicely cancel, I can still keep that 2n to the power of n multiplied by 2n raised to the power of minus 1, maybe. Or actually 2n to the power of minus 1 multiplied by 2n to the power of plus 1. So maybe this way I will be able to cancel, because that's my goal. So now I write down the actual nth term. So that's be n over n plus 1 times. So I just copy in this term, which is in brown, without the minus sign. So it would be 2 times x. I should put x. I should be careful. X here and x here. So 2 times x in the parentheses raised to the power of n minus 1, just like we had hopefully in numerator. And that's it. So this is the limit to find when we also do the absolute value of this whole thing. So time to cancel, that's what I was actually preparing for. And then we're gonna see what's left, right? And do a little bit of algebra. So we get in a limit of now my fraction from denominator is gonna flip. So we're gonna have n plus 1 times another n plus 1 on the top, and n times n plus 2 on the bottom. Okay. It looks like by the L'Hopital's rule, I definitely be able to take care of this limit when n approaches to infinity, because the other piece is just to 2x. So that's the part that I care about in terms of absolute values. So the actual limit here will be number 1, is it? If you look at the leading coefficients, then this whole thing approaches to 1, isn't it? You say, you sure? Well, distribute, you will be sure. N squared plus 2n plus 1 is on the top, and n squared plus 2 n is on the bottom, and the quotient of leading coefficients is our limit, so it's 1 over 1. Or if you take derivative twice, you will see that by the L'Hopital's rule, since n approaches to infinity. So the point of story that this needs to be less than 1. And that's my inequality that turns into 2x being from minus to plus 1, or x is in between negative and positive 1/2. So that's when we have the absolute convergence for the series, convergence in absolute values. And I need to now check and see what happens when x is equal to plus 1/2, and also what happens when x is equal to negative 1/2. Because my series is going to converge on the outside of this interval, but what happens when we have the end points? And what happens with our original series, which is here? So let me replace my letter n with letter x with 1.
Well, Elliot,
Okay, let me carefully do this. It looks like we're gonna have the power of n minus 1 here. And notice that this is just a sign alternating series, right? Sign alternating series with its nth term that approaches not to 0. So it's going to be divergent. Agree with this? Or not really? So series is here, n over n plus 1, and its nth term is not going to 0. Right? Its nth term does not approach to 0. That's why series is divergent. Well, that's great to know. So what happens with the other case? Well, I got a feeling the same exact thing happens with the other case, right? Because we also going to have this n over n plus 1 structure for the case when x is negative 1/2. And now we're going to multiply -2 by negative 1/2. So this is going to be just a positive number 1. So the factor is going to be just times 1. But again, the series is divergent, right? And that's why at the endpoints, we don't have any equal signs, and that's why the series will converge only at numbers greater than -1/2 and less than +1/2. At the endpoints, no convergence. Just like that. So these are, I guess, lengthy exercises, but it could be a good type of a question for the final, because remember, for final, I should ask you a couple of questions, and I guess exercise of this type that has a few steps in it could be a good type of a question. There's nothing really tricky and special about it, standard problem. So anyways, try to do some more exercises in this section, the last section that I needed from chapter 9. So we can move on. And for now, we skip rest of 9 with some series that these problems are quite tedious. And they decided not to consider them at all in calculus 2 class. So that's why you can just legitimately skip those. And we move to chapter 10. That just deals with more calculus for cases when you don't have functions. Like nice examples of not functions are the ones that called ellipses, like we have here, and then their friends, circles. There are some hyperbolas here, some parabolas as well. But I guess the key part is to start looking at the section 2 of chapter 10 that enables us to deal with the non-functions. Because we used to work with functions, we always call f of x, the derivative, antiderivative, but what if you don't have a function? And that's where chapter 10 starts. For the final, that's a good question. I plan to give you a final on Tuesday. So that way we'll be on a safe position, because Thursday we have another day of class, and on Thursday, which is going to be in the first week of May, I should have all your grades already calculated and posted on the Canvas. So you will know what you got on the class before that Thursday. Of course, if you turn in the final, if something happens, if you can't turn it in, well, I will keep bugging you with emails asking, so where is your final? I want to grade your final, send it to me. So I think it never hurts to have an extra reminder. Sometimes it is important. And also, I'll give you a chance to fix things. Just like with midterm. Remember, if you didn't like your midterm grade, you could have got it a little better by 1 grade if you redo it. So I plan to do the same thing with the final. So if you happen to mess up on the exercise on the final, I will also give you a chance to fix that. And that's why I think it's a good idea to give it a little earlier so I can look at it, put grades on the canvas. And if you don't like your grade, I can always tell you what to do to fix it. I think it'd be always a good idea, right? So that's why I give final on Tuesday, which, as you say, is 2nd, right? May 2nd. And that's going to be in 3 weeks, right? In 3 weeks from today. So we have plenty of time to prepare. And I also have homework due, so we'll see what we cover from chapter 10. And all that I hope to receive on Tuesday. Well, if not, I'll give a little extension because I can regrade or wait, and we can always come up with something that works for you. Because everything works for me, as long as I turn in grades before their deadline. That's why I try to give it a little earlier, so everyone will have plenty of time to send me work, and I guess that way we'll go with this class. So anyways, I'm glad that you care about this final exam day, and let us start talking about chapter 10, that again deals with relations, not just functions, but relationships on variables x and y. So picture we have here in 10.2, I guess, is not really needed because that's a function. So with functions, we know how to work pretty well. But in example 1, we don't have a function. We have a relation. But such a relation that x coordinate and y coordinates of this relation are both functions. Notice that here I have a function, they call it as x of variable letter t, and the other function is y of variable letter t. So when you have some type of relationships on x and y coordinates that you cannot use previous methods we learned so far, what you can do is parametrize. That's why this section is called parametric equations. So x coordinate will be function of parameter t, and y coordinate is also a function of parameter t. Interesting. And that way you can work on those two functions separately, find their derivatives. When derivatives are 0, that's what we're always doing, right? Take derivative, set it equal to 0. Take second derivative, set it equal to 0. And that's pretty much all we're going to do in this chapter 10 as well. Use methods of Calc 1 to nice functions. Functions will be nice for beginning with parametric equations. And then we'll be able to get anything we want. So section 10.2 introduces us with parameterization that could be done various ways. It is up to you how you parameterize those functions. So if in example 1, they gave me x, which is t squared minus 4, and y equals to t over 2, then what I can do is pull out t here. So I can say that t is equal to y multiplied by 2, right? If I multiply by 2 both sides of this equation, and then replace my parameter t in the other equation, and I'm going to get the actual relationship with my x and y coordinates, so I can see where this is actually coming from. So 4y to the second power minus 4 is a relation which is not a function, right? Because it has a y squared present in it. It's just like a analog of relation x is equal to y squared, like a parabola that x root y. Parabola that opens to the right. And that's why it's not a function, because it has like two pieces, basically. But what they did, parametrizing, produced two equations, and each of them is functions, so I can use my old methods. And I say, Alex, they also restricted, looks like, your values. They said that parameter varies from -2 to +3, so they didn't take this entire relation, but they got just a part of it that started someplace and then ended at some place as well. Why would they do this? Well, I guess just to show you that various possibilities could be utilized, maybe for a real life applications, it makes sense, because technically otherwise there is no really reason to restrict parameter. But again, in applications that happens. And again, you can parameterize your function any way you like. And as I said, sometimes it does make sense to parameterize and sometimes it doesn't. Like, looks like in this case, on the figure that has like a portion of parabola that opens down, you can say just something like maybe y is equal to minus x squared plus 1. So there is no really need to parameterize because you have a nice function of x squared. So they probably actually reduced it, right? So we can see the graph and right away tell the equation. But after all that mess with isolating parameter, just like I did here, so I pulled out parameter from one of the equations and plugged this into the other equation, because that same thing they did as well, but with different letters. So you produced another parameterization. Ellipse or its friend circle, people always parameterize with cosine and sine. So here's the way to parameterize the ellipse. So 3 times cosine for x coordinates. Notice that instead of using cosine for circle, they tripled it. And then 4 times sine for y coordinates, so they multiplied by 4. That's a pretty standard way of parameterizing the equation of ellipse that looks like that. Notice that again, it's not a function because it has y squared in it, right? So they have this nice way to parameterize. And that's what they're playing in here. They parameterize various relations and functions. And I guess in the section 10.2, we just get a little flavor for that. So you're asking next Tuesday? No, it's on the first week of May. It's not, the final is on the first week of May, according to a schedule of classes. Next Tuesday is going to be what? Just April 18. But first week of May is May 2nd. So it's 3 weeks from today, not 1 week, three weeks. So just hold on, but you will get it. I know that some people are anxious to be done with this, and I totally understand you because it's been too long of semester, but we still have a few nice things to learn. So let us look at them, because I think this is exciting material that will be utilized in later classes when you work with very complicated curves, some kind of not functions. But when you be able to describe its x and y coordinates separately with some parameter t that usually stands as a time. So with respect to time, x coordinate is given as function and y is also given as function. Well, then you get the so-called parametric equations. So anyways, let me do some problems here. So how about if I try problem, let's say number 9. Again, I know it's unusual to write functions in this format, but we just want to get used to this a little by little. So if you have your x and y coordinates given somehow like that, then they say, can you actually graph this curve? And since we're experts in graphing functions, then why don't I turn this into actually function y of x by, say, squaring both sides in my first equation, and then replacing the parameter with x squared, right? Instead of parameter with x squared minus 5. But I should be careful, because if I graph x squared minus 5, the parabola here, then notice that when I square something, I always pick up extra solutions. So what are we talking about? Well, if I have, let's say, x equals to 2, and if I square both sides of these equations, then I also picked up x equals to -2. You see? So you should be careful when you squaring, and actually looks like x is going to be automatically non-negative, because when you square root real numbers, then we get only positive values, right? So my x coordinates can only be positives. That's the restriction on x. So I actually have only right branch of this parabola. How can I say it? Well, I should say that x is non-negative, just to be careful. So there is a little extra in all of these problems. You need to watch out for the squaring of both sides. In other words, you need to watch out for domains of the functions. So, or ranges. So just always concerned with this, because otherwise, if you didn't turn this into the way we used to see it, then you would need to go through the pain of getting all of these little points like we did back in the arithmetic class. So they do that here. So produce various values of parameter, and then based on those values, so they like 0, 1, 2, -1, -2, then they calculate on the x and y coordinates, and that takes a while, right? And you can always enjoy this over a weekend if you have nothing else to enjoy. So, but our goal is to always find the most efficient way to do things. So let me look at other exercise here. How about 18? Looks a little different. Let's try 18. So check out questions, see which one you want me to consider, and we'll tackle it. So x coordinate is tangent. squared of theta, and the y coordinate is secant squared. So now I need to try to put some type of a relationship on x and y. And what I can recall is that 1 plus tangent squared is equal to, remember, secant squared. Pythagorean theorem that I can actually utilize in here. So if I have such a relationship, then tangent, I'm going to be able to replace with x, and secant replace with y, because this works for any angle theta. So we have a nice relationship with 1 plus x is equal to y. And this is nothing else but the equation of line, right? But once again, I have to watch out, see if there are any restrictions, right? So notice that these two are both squares, so they are non-negatives, nx and y. And there'll be some more. So I just need to consider the portion of this line when both of them are non-negative. So it looks like this is the part here, right? Also, remember the graph of function secant? It deals with the y is equal to 1, right? That's the bottom, and -1 is also present. Secant is 1 over cosine, right? So I need to recall the graph of function cosine to help me with this. Function cosine looks like that piece up to 2 pi. Right? So the point of story, when I square the pieces of secant, there'll be no lower side, just the upper side. So there'll be only here. So the lower piece is gonna reflect up and so forth. So what I'm doing is trying to see the possible range for this function, because it looks like the main can be anything, but for the range, we'll get greater than or equal to 1. So actually y is greater than or equal to 1. So y coordinates are greater than or equal to 1. And that's fine with our description. So this piece of line is still present. And well, I guess I got a graph. So I sketched the graph of this real unusual function, right? And I guess using various values for theta will take you forever to calculate and to eventually come up with a line. So that's why we always try to find the relation on our x and y coordinates. And of course, yes, there you could look at the exercises and the sections, and you can probably find something real nasty that you can't find any relations on, and that you have to actually plot point by point. But believe me, we're not going to work with these things. It's just a little bit too much, because each textbook has its own specific exercises that author is very proud of, and masters those from edition to edition, comes up with new tricky problems. But that's not the standard material for calculus 2. Our goal is just to be able to describe those relations and then graph them, and that's pretty much all we need in this section. So let me try one more, and then maybe you can try one. Something very standard. So maybe I can do the problem number 6, and you can try then problem number 5. I think that'd be fair. So I know you cannot graph, but you could just produce the equation, and that should be good enough, because I'm sure you know how to graph equations, right? So 2t squared. So what you're going to need to do is just to produce one relation on the variable letters x and y. And in order to be able to do this, I want to pull out my parameter. Or actually, I'm not going to really pull out this parameter, since I want to relate x and y. I just want to kind of eliminate this parameter. So when I'm looking at the first equation, then I can see that t squared could be taken out and then replaced into my other equation. So we're going to have a t squared squared. So I'm going to have x over 2 to the power of 2 and plus 1 for y. So notice that t is eliminated, and I have a relationship with my variables x and y. And at that stage, I can definitely graph the parabola-like curve here, but there could be a bit of a restriction, right? So what is my restriction? Well, this is definitely greater than or equal to 0 because t is squared. So I'm gonna think of the graph of parabola that is having the y-intercept at point 1, right? It's a little bit wider. And then, so that's the graph. And then I want to make sure that my t squared is going to be positive. So x coordinates are also going to be positive. And that's what makes me have just this happen. So people say x is greater than 0. I say, Alex, and y is also greater than 0. Yeah, looks like it's actually greater than or equal to 1, but looks like automatically we get it because this parabola is at point 1. So it's a little first flavor of parametrization, and next time we're going to take derivatives of these ingredients. We'll move to the calculus part. So how about if you try to relate x with y in a little quiz? Should be pretty much same thing as I just did. So exercise 5, please find the relationship on variable x and y in one single equation. Looks like you could just replace x with parameter or y with parameter. So you just want to pull out t and put it in the other equation, and that's all you need to do. So no t, just one equation, just like I did in this exercise. So you don't have to sketch any graphs. You can't really do this, but find y function of x. And I kept doing it in the exercises. I found the function here or function here, right? So it's same for all. So please take your time and put the answer in the chat as usual, and then you can relax and enjoy the rest of the night.